All right, so the next little section that we're going to get into in Chapter 9 is dealing with the conservation of momentum. And we'll start by taking a look at a pre-lecture video. All right, and in this video, he does a couple different demos, but one of the main demos he does is, you can kind of see it here, there's this water bottle, that's not a good color, there's this water bottle car, this jet car, inside of this fish tank, and he asks a few questions about how the fish tank's going to move as the jet bottle car explodes, essentially, and pushes the water back. So it's a really interesting question, and we got to think about what's happening in the system and stuff like that. So it's a really great demo to check out. I'm not going to ruin anything for you. You're going to go watch it if you really want to know. So go watch that video if you want to know what happens. But the section 9.4 is on the conservation of momentum. And much like energy, which we talked about before, energy is conserved. So the initial energy has to equal the final energy if the work equals 0. It's the same thing right now. The initial momentum, which is a vector quantity, is going to equal the final momentum if the impulse equals 0. So a very similar concept that we've already discussed and talked about. It's just, actually it's easier now because we're just looking at momentum and not all these different types of energies. Okay, so conservation of momentum. I have these two spheres over here on the right side of the screen, sphere 1 and sphere 2. They're moving towards each other. They hit each other. When they hit each other, there's a collision. And according to Newton's third law, they exert action-reaction pairs of forces. So therefore, then the balls will bounce off each other and go their respective directions. Now, how fast they go in their respective directions is a concept that we're going to cover with conservation of momentum. So in this example, though, let's say, for example, that ball 1, it was going at like 3 meters per second or something like that. And now it's going at 4 meters per second. Well, I don't know their masses, so I can't really calculate exactly what their momentum is, but let's assume that they're the same mass. So they're going to have going towards each other. Then that mass or that velocity will actually get transferred. So this one will now be 3 meters per second. And that means that this one was coming in at 4 meters per second. And that's because the momentum has to be conserved in that direction. And that's one of the implications and applications of the conservation of momentum. So there's when any two objects hit each other, there's no change in the total momentum of the system, no matter how complicated the forces are. So I could have, over here, I can have object 1, object 2, and object 3 kind of all colliding at each other at the same time, but there's no change in the total momentum of the system. It's conserved, just like we talked about with energy. The only thing that changes it is if we have an impulse or a force exerted to add momentum or to remove momentum to the, from the system. So my big analogy is, think about when you're playing pool. No matter how complicated a combination shot you're going to make when you're playing pool, if you're hitting one ball into another ball, into another ball, into another ball, to try to hit into another ball to get the ball into the pocket, the total energy initially came from you hitting the cue ball. The total momentum comes from you as well. You're exerting a force on that cue ball over time. If you hit a ball and the cue ball goes to the right, the other ball will have to go to the left. That will conserve momentum. So one object goes to the right, the other object goes to the left. It's a conservation of momentum. So here's a quick check. You awake in the night, the middle of the night, to find that your living room is on fire. Your one chance to save yourself is to throw something that will hit the back of your bedroom door and close it, giving you a few seconds to escape out the window. You happen to have both a sticky ball of clay and a super bouncy super ball next to your bed. Both are the same size and the same mass, but you only have time to throw one. Which one will it be? Now, the majority of people, when they see this question, they instantly say, I will throw the ball of clay. And they say that because, well, if I throw the ball of clay, it'll stick to the door, and then it'll go forward. The door will close. And that's not wrong, but it's not the best choice. See, when you throw a ball of clay, the clay has some momentum. It sticks to the door, and that increases the mass. It'll decrease the velocity, but it'll have some final momentum. However, when you throw the super ball bounces off the door. So the super ball has a larger change in momentum because it has an initial positive velocity and then it goes to a negative velocity. So if it's got a larger change in momentum, that means the force exerted on the door over the time will also be larger, and it'll close better than the sticky ball of clay. So kind of a really weird example problem, but that's the technical correct answer is a super ball. And hopefully, if you remind me, I will show you a demo in class that will actually confirm this choice. All right, mosquito and a truck have a head-on collision, splat, which has the larger change in momentum. Give you a second to think about it. And once again, we jump to this mosquito concept because it has a huge change in velocity, and that would be incorrect. They have the same change in momentum. And the reason that they have the same change in momentum is because they experience the same force over the same amount of time. Now, the momentum is mass times velocity. The mosquito has a very, 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 very small mass, so it has a huge change in velocity, whereas the truck has a very, 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 very high mass, so it has a very small change, or AKA a measurable change in velocity. And of course, there is the age-old question of what is the last thing to go through the mosquito's brain when it gets hit by a truck, and that would be its ass. So the law of conservation of momentum is very simple. The total momentum of an isolated system is constant. So interactions within the system don't change the momentum. It's only when you have an impulse or a force exerted over time that can change the momentum. Okay, so our simple equation is that our final momentum has to equal our initial momentum whenever we have a collision, unless there's an outside force. So a huge and awesome example of this is the Newton's cradle. And Newton's cradle, it's literally one of the simplest things in the world, but it's a really cool application. And I will potentially blow your mind with this really stupid demo. All right, so we got an example problem. So two ice skaters, Sandra and David, they stand facing each other, and they're going to push off each other. And yes, we're obviously going to do this one in class, but this is a type of collision. Actually, as awkward as it is, technically, we'll talk about this one more later, but this is an explosion. And my question for you is, in the before picture, David's at rest, Sandra's at rest. How much momentum do they have? And the answer is 0. They start with no momentum. So afterwards, that means that they also have to have no momentum. And that doesn't make sense because we know that Sandra is moving to the right at 2.2 meters per second. But David, and we'll talk about this in class, is moving to the left, which means he's moving in the negative direction. And those two momentums are going to cancel out. We'll have another partner problem, again, standing at rest on a skateboard, and then Ryan, some outside person, is going to be a jerk and throw a 3-kilogram ball at him, and we'll see what happens. All right, so this is what we were just talking about. An explosion is when the particles of the system move apart for a brief, intense interaction. God, I really hope that's not the way we describe David and Sandra, a brief, intense interaction. So an explosion is the opposite of collision, but it's still an isolated system, so the total momentum is still conserved. So here, for example, on the right, we have a rocket ship, and it's got fuel, and it exhausts out that fuel in terms of gases by burning it. So it pushes down, so the total momentum, or so the rocket ship can go up, but the total momentum will still be 0. It's still an isolated system. All right, got another quick check. So we got two boxes on a frictionless surface. They had been sitting together at rest, but an explosion between them has pushed them apart. How fast is the 2-kilogram box going? Well, This has 8 kilogram, I'm sorry, this has 4 kilogram meter per second going to the left, which means that there has to be 4 kilogram meter per second going to the right, which means that 4 divided by 2 is going to be 2 meters per second to the right, right? So the momentum has to be conserved, which is just mass times velocity. Super easy. Another one, here we have a hit and stick. We'll talk more about collisions as we get one more section into this chapter. It hits and sticks. So it starts with 3 kilogram meter per second, which means that it has to end with 3 kilogram meter per second. However, now it's going to have a mass of 1 kilogram plus 2 kilograms. So it's going to have a total mass of 3 kilograms. So it's only going to move at 1 meter per second. Another partner problem that we'll talk about, this is a spring-loaded toy gun. So yes, this is a okay to talk about in school question. The bullet shoots, or the ball it shoots forward at 15 meters per second. Then the rifle, the toy rifle, is going to have a recoil velocity. How much is that recoil velocity? We will use a conservation of momentum to solve this problem. And that's your little introduction into conservation of momentum. We'll do these example problems in class, but it's just like conservation of energy. Momentum is not created or destroyed. It's always conserved unless there's an impulse or an outside force acting upon it, which is literally the exact same thing we said about energy. Energy was force times distance. Momentum is force times time. Slightly different, but a great way to analyze collisions, and we will do that even more in future segments.